trying to map the exact discrete steps of a stochastic optimization algorithm is, well, it's a bit like trying to track the precise erratic trajectory of a single water molecule in a boiling pot.
Right, because you're tracking the microscopic noise of every individual data sample. It just bounces around the loss landscape.
Exactly. It's jagged, it's mathematically overwhelming, and honestly, you often end up missing the macroscopic flow of the algorithm.
Ah,
But Junchi Li's April 2024 paper proposes something pretty wild.
it really does. If you speed up time, zoom out, and look at the continuous fluid dynamics of the system, the chaotic alchemy of tuning hyperparameters actually collapses. It becomes a perfectly predictable equation.
Which is incredible. Welcome to this deep dive where we're unpacking this unified algorithmic framework. If you're dealing with modern industrial-scale machine learning problems, specifically regularized empirical risk minimization over massive distributed datasets, you already know stochastic alternating direction method of multipliers is your default choice.
Yeah, SADMM handles streaming data and distributed constraints beautifully in practice. But, the theoretical side has always lagged behind the empirical success.
Because analyzing the discrete time dynamics of stochastic algorithms is notoriously difficult, right?
Oh, absolutely. The proofs get messy, the variance bounds are tricky, and choosing the right penalty or relaxation parameters has historically been based on, well, intuition and trial and error.
Just pure instinct.
Yeah.
But this paper introduces generalized stochastic ADMM, or GSADM. We're going to detail how these discrete sequences weakly converge to a continuous time stochastic differential equation.
Right, and by translating the algorithm into a continuous space, we finally see exactly how the variance scales. We can mathematically prove why certain hyperparameter choices are strict requirements to prevent the system from diverging.
But before we transition to continuous time dynamics, we first need to establish exactly what we are transitioning. We need a single framework that encapsulates the chaotic landscape of ADM variance.
So, to appreciate that continuous time dynamic, we have to look at the fragmentation in the discrete world. The core optimization problem here involves minimizing an objective function, Villerex Iplis, fx plus gax.
Okay, so fx represents your expected empirical risk.
Right.
The expectation of your loss function over the noisy data.
Exactly. And the second term, gx, is your convex penalty or regularization term, which is subject to a strict linear constraint. The classic ADMM approach splits this problem.
It alternates between updating the main variable's dollars, then a constraint variable Zeller, and finally a dual multiplier.
Right, the classic triplet. But over the years, engineers have duct-taped countless variations onto that triplet to bypass specific bottlenecks.
Like if the sixth update is too computationally heavy, someone introduces linearized ADMM to approximate the expected risk.
Yeah, or they drop into a gradient-based ADMM where they just take a single cheap gradient descent step instead of fully solving the subproblem. So we ended up with this highly fragmented landscape of distinct algorithms.
Which brings us to Li's grand unification. It's like finding a grand unified theory for stochastic optimization. He brings all these variants under a single roof using a few explicit mathematical dials.
Those dials are parameters built directly into a generalized objective function for the 6-per subproblem. You have explicitness parameters, a megadollar runteller, and a mega acting as binary switches.
And you've also got a proximal parameter, a penalty parameter and teller, and a relaxation parameter alpha, right?
Exactly. The beauty of this generalized objective function is how it manipulates the augmented Lagrangian. For instance, omega $1 controls how you handle the expected risk.
So if you set omega dollar to 0, you're demanding a full implicit solution for the noisy objective.
Yeah. But if you flip omega $1 to 1, the framework instantly swaps that heavy computation for a linear approximation. It just uses a single noisy gradient evaluated at your current step.
So if I'm an engineer tuning these dials on a cluster, I can seamlessly shift gears. By just tweaking these omega teller dials, I can recover the standard online ADMM.
Right. Or you can morph the system into an accelerated linearized ADMM or drop into a gradient-based ADMM, all without changing the underlying mathematical architecture.
It just integrates the stochastic gradient from a MIDI batch, applies a quadratic proximal penalty so the update doesn't fly too far, and moves to the next state.
Exactly. It creates a unified discrete equation. But analyzing that discrete equation globally still leaves us stuck tracking that chaotic water molecule we mentioned earlier.
Right, because discrete stochastic paths are jagged. They're hard to analyze globally. So how do we fix that?
We speed up time. The paper shifts into the scaling regime, moving from discrete steps to a continuous flow. We take the penalty parameter and drive it toward infinity.
And in ADMM, Pertar dictates how heavily you penalize constraint violations, right?
Yes. As stray gets larger, the algorithm takes functionally smaller steps. So the paper defines the step size analog as epsilon, which is just the inverse of Hercafine.
Oh, I see. So as Hazard approaches infinity, epsilon approaches 0. And we scale the proximal parameter linearly with 1, so their ratio, ace-nullers, stays constant.
Right, we enter the small step size regime. But making the leap to continuous time with stochastic noise requires Milstein's weak convergence theorem.
Because you can't just take a standard limit, like in deterministic calculus. The exact path changes every single time based on random data samples.
Exactly. Weak convergence bypasses this by tracking the probability distribution of the paths instead. It proves the sequence of discrete states admits a continuous limit, $6, solving a stochastic modified equation.
And the exact stochastic differential equation derived in the paper is beautiful. It's driven by a deterministic drift term pulling you down the gradient, and a diffusion term representing the stochastic noise.
Yeah, that diffusion term is scaled by the square root of your step size epsilon. And modifying both forces is a matrix, which is scalar times the identity matrix plus the term involving alpha and omega times transpose of $.
It basically acts like a steering wheel, reshaping the geometry of the space you're moving through. But here's where it gets really interesting, but also a bit puzzling.
What's that?
The profound discovery is that this SDE looks essentially identical to preconditioned stochastic gradient descent. It abstracts away the distributed constraints entirely.
It does. The matrix acts entirely as a preconditioner on the gradient field.
But wait, the original ADMM updates $6 and the multiplier too. This SDE only models $XD. Where did the constraint variable Zelger go in the continuous limit? You can't just lose parameters.
What's fascinating here is a technique called dominant balance. When you expand the optimality conditions using Taylor series, the one-step difference for the main variable intrinsically incorporates the residual, the error between $6.60.
Oh, so the error from the constraints feeds directly back into the trajectory of the main variable.
Exactly. Think of the main variable sextity as a heavy truck navigating the landscape, and the constraint variable Zellers as a trailer hitched behind it.
Okay, I like that. Yeah. So in the discrete world, the trailer bounces around independently. There's slack in the hitch.
Right, but as you speed up time and drive one odor to infinity, that hitch becomes completely rigid. The truncation error forces the triplet iteration to collapse.
Meaning the trailer is entirely slave to the path of the truck. The entire effective dynamic is restricted entirely to the Zixel component in the continuous limit.
Yes, the continuous dynamic of a Zixel is mathematically proven to be just a linear transformation of Zixelers, plus a tiny negligible error governed by epsilon.
That is incredibly powerful. You don't have to worry about the constraint variables flying off the rails independently. Their stability is tethered to the main variable.
Exactly. And speaking of stability, we now have this beautiful continuous equation, but its real power lies in what it reveals about the noise inherent in the system.
Right, how hyperparameters constrain that noise. The SDE has a diffusion matrix, sigma capturing the variance of the stochastic gradients.
And using Ito-Taylor expansions, the paper proves that the standard deviation of both 6-Keller and 6K is exactly at $.
Which is equivalent to $12. So the larger your penalty parameter, the tighter your algorithm hugs the deterministic path. It throttles the fluctuation.
That's right. And this sets up the framework to solve one of the oldest mysteries in empirical machine learning, the relaxation parameter, alpha.
Yes, the alpha enigma. Practitioners have known since the 1990s that alpha must sit between 0 and 22. Often they favor over-relaxation, like setting alpha greater than 1 for speed.
But for decades, it was essentially alchemy. We knew the boundary was 2, but a strict theoretical proof of why it explodes past that point was missing.
So how does the continuous time formulation expose this?
Well, the paper demonstrates that as alpha approaches infinity, the residual at any given step roughly equals $1 alpha multiplied by the previous residual plus an epsilon error.
Oh, wow. So for the constraint residual to geometrically decay to 0, the absolute value of $1 alpha mathematically must be strictly less than 1.
Exactly. So what does this all mean? We aren't just guessing that alpha between 0 and 2 works well anymore. The math literally dictates it to prevent the constraint residual from blowing up.
Because if you over-relax to 1.5, you overshoot the optimal step, but it still decays. But if alpha hits 2, the multiplier is max at 1.
Right. You constantly correct and overcorrect with equal force, and the whole system diverges.
But wait, what happens to the residual when alpha is exactly 1 versus when it's relaxed? Does it scale differently?
That's a great question, and it's covered in Proposition 7 of the paper. When alpha equals 1, the raw residual converges incredibly tightly. It becomes vanishingly small, scaling at live epsilon dollar.
But when you introduce relaxation to gain speed, you lose that tight scaling.
Unfortunately, yes. When alpha NECA 1,1, the raw residual degrades and scales at epsilon dollar, you create a trade-off between convergence speed and constraint accuracy.
So relaxing the algorithm inadvertently makes the constraint violation an order of magnitude worse relative to the step size?
Yeah, but the paper introduces a brilliant workaround, the modified alpha residual. By linearly combining the raw residual with the step-to-step difference of solars, it cancels out the truncation errors.
Oh, so this modified residual maintains that tight epsilon co-scaling even when you relax the algorithm.
Exactly. It lets you use over-relaxation for speed without sacrificing the theoretical bounds on your constraint error.
That's elegant on paper. But for data scientists and engineers listening, the ultimate test is empirical validation. Does this framework predict real-world model behavior?
It really does. The author ran extensive validations, starting with a non-convex toy example and 6/4 loss, and moving to generalized ridge and lasso regressions.
But wait, computing the exact diffusion matrix for an SDE requires evaluating the gradient over the entire massive data set at every tiny step, right? That's computationally devastating.
It is, which totally defeats the purpose of stochastic optimization. So they approximated the covariance matrix sigma using a sample version.
And how many samples did they need to get a match?
Just 111 random samples per step. That was enough to achieve a near-perfect match between the discrete SADMM trajectories and the SDE mean and variance predictions.
Wait, really? Just 9 samples accurately captured the macroscopic flow of the whole distributed system?
Yeah, it validates the robustness of the weak convergence approximation completely, and they also tested the consequences of over-relaxation.
Let me guess, the continuous model predicted the exact trade-off practitioners experience.
You got it. Over-relaxation fundamentally shrinks the precondition matrix Sax-Hatchery. Since steers the deterministic drift, shrinking it accelerates the descent to the true minimizer.
But there's a catch, isn't there? That same preconditioner matrix sits in the denominator of the diffusion term.
Exactly. So while over-relaxation accelerates your drift, it also amplifies the stochastic fluctuation. You reach the bottom faster, but you bounce around the minimum with far greater violence.
Which leads right into section 5.3 of the paper, the two-phase behavior of stochastic training. The SDE framework rigorously proves a distinct transition time, $2.
Right. Think of the first phase like dropping a boulder down a mountain. Gravity, the deterministic drift, overpowers any small bumps. The path is highly deterministic.
But eventually, the boulder reaches the valley floor at time $2. Gravity becomes negligible, and those small bumps, the stochastic noise, take over.
Exactly. In the second phase, the fluctuation term completely overtakes the drift. This implies standard acceleration techniques are doomed to fail in the saturation phase because they amplify noise.
This is a brilliantly precise model, but if you're an engineer training a model right now, how do you actually use this Tato transition point? You can't just run an infinite batch continuous SDE.
Well, if we connect this to the bigger picture, engineers can use this analysis to program adaptive learning rate or batch size schedules.
So they monitor the ratio of the objective functions lost to the calculated variance. They measure whether drift or diffusion is winning.
Exactly. But explicitly balancing the variance against the objective value, algorithms can autonomously trigger an intervention the exact moment Taylor is crossed.
So the system could autonomously increase the preconditioner matrix at hell or drop alpha closer to 1 to tighten the variance.
Or dynamically scale up the batch size beta to suppress the noise right when it begins to dominate. It turns adaptive scheduling into a rigorous feedback control problem.
That is just a masterclass in using continuous limits to bring order to discrete chaos. To summarize our journey today, Junchi Li's paper isn't just another tweak to ADMM.
No, it's a comprehensive translation of discrete stochastic ADMM into a continuous stochastic modified equation.
It reveals that all these fragmented variants are fundamentally governed by preconditioned stochastic gradient descent. It proves why alpha must sit between 0 and 2.
And it accurately models the standard deviation of the noise scaling, providing a real mathematical roadmap for optimal control policies.
Which leaves us with a pretty provocative thought. We spend so much time designing discrete machine learning algorithms and struggling to prove they converge.
Right, cobbling together new variants for specific bottlenecks.
But what if the future of optimization is reversed? What if we first design the optimal, perfectly controlled, continuous stochastic differential equation for our specific data constraints?
And then discretize that perfect equation into a bespoke algorithm.
Exactly. Instead of trying to track that chaotic, jagged path of a single water molecule, what if we just design the perfect fluid flow and let the algorithm pour it? Thank you for joining us on this deep dive.